The rate of chemical reactions in a battery is responsible for the power a battery can deliver. Typically, these reactions happen with growth of material at the electrodes of the battery, such as in lithium-ion batteries and lead-acid batteries. Here we want to find out what mechanisms are responsible for the reaction rate of the chemicals. In that regard, to recall, imagine that you are working in a building at the second floor with several colleagues. Once it is lunchtime, you all go to the canteen, which is in another building across the pedestrian area. There is a little summer breeze and the sun is shining. Now think about what you experience in terms of flow of people going to the canteen. You stand up and you walk to the elevator, escalator, or steps to go down. There people pile up. You arrive in the atrium or central hall and leave the building through a door. Again, people pile up. The sun is shining and there is a little breeze, so you are looking for your hat and sunglasses. People are accumulating just outside the door and moving slowly to the middle of the street. There are people moving easily to the other side of the street till they arrive at the other building. People are taking off their hat and sunglasses, which takes some time. Then they must go through a door to get into the building. Once they are in the building, they must find their way to the canteen. And finally, when they are in the canteen, they must line up for the buffet and cashier. This is exactly what ions are also experience once they go from one side to the other. So let's see how this works in, for instance, a vanadium redox flow battery. The discharge reactions that occur in a vanadium redox flow battery are vanadium 2+ ions to vanadium 3+ ions. The electrons that are being released go to the positive electrodes, where vanadium 5+ goes to vanadium 4+. But let us concentrate on the discharge at the negative electrode, where vanadium 2+ will consumed and vanadium 3+ will be formed. The vanadium 2+ ions are in the bulk, as the people crossing the pedestrian area. This concentration of ions is everywhere the same, and migration here is determined by ohmic behavior, also called drift. This is usually assigned as conductivity and indicated here with a K. From there, these ions have to migrate to the surface to donate the electrons, and this happens through a layer where accumulation occurs of the species, similar as those people waiting at the door to enter. This mechanism is a process that is called diffusion, and here assigned with a D. This diffusion layer is known as the Guy-Chapman layer. This layer is just a few nanometers thick. Once the ions arrive at the surface, they absorb and donate the electrons, similar as the people picking up their food and pay. This is the electron transfer reaction, as is assigned here as R0. This adsorption layer is known as the Helmholtz layer and is in the order of a few angstroms, obviously roughly the sizes of a few atoms. Then the new vanadium 3+ ions must leave the surface through the diffusion layer, going back into the bulk. This means we have split up the overall mechanism into conduction, diffusion and reaction rate. This kind of mechanism will also happen at the positive electrode and actually is very general for all kinds of electrodes in batteries. The diffusion and reaction are time-dependent processes and therefore will influence the power performance. So if we plot the measured voltage versus the current and thus the power, we can identify indeed these three different mechanisms. At low power, low current demand, the overall mechanism is determined by the reaction rate, assigned by activation losses. By asking more power, the conductivity of ions in the bulk will play a major role, also known as the ohmic losses. Once we further increase the power demand, the ion starts to deplete and therefore diffusion limitations occur, here referred as transport losses. A similar curve constructing for lithium-ion batteries is rather difficult. It is therefore that the power rate is shown here as voltage versus capacity curves at different discharge rates. But it doesn't mean that the mechanisms are not taking place. They still are there. Now let's see how these various mechanisms can be analyzed in terms of equations so as to provide the possibility to calculate the power limitations. Without going into too much detail, the reaction rate is determined by the well-known Butler-Volmer equation. This equation describes the electron transfer determined by how many electrons are being donated minus how many electrons are being accepted, thus reflecting the anodic and cathodic current. In this equation, A is the electron transfer coefficient, Z the number of electrons involved in the reaction, F the Faraday constant, N the overpotential, R the gas constant, and T the absolute temperature. Focusing now on the anodic current only, we can approximate the current into a low overpotential part and a high overpotential part. At low overpotential, the behavior can thus be approximated by a kind of ohmic behavior. But at higher overpotential, we have to take the exponential part into account. As was shown for the vanadium redox flow battery, once we add more power, the overpotential also increases, and thus we will arrive at the ohmic behavior of the bulk electrolyte. The current then goes linear with the overpotential, according to Ohm's law. When the power demand is even further increased, the reactive species are no longer able to arrive at the electrodes, and we may expect diffusion limitations. Here typically the current goes to the square root of the overpotential as explained via Fick's law. If we know all the parameters for those equations, we can construct a so-called tafel plot. This tafel plot shows the logarithmic of the current as a function of the overpotential. What has been shown here is an example how such a curve could look like. Each mechanism gives a certain current voltage profile. It is however stressed that the current we can expect is limited by the lowest current of either of these mechanisms, which is shown by the red dotted line, and thus it provides us information on the maximum power we may expect from the electrode, but rather with the other electrode also from the whole battery. It is this what researchers are analyzing and measuring to find out where we can further optimize the battery. The surface area to reduce the overpotential for reaction and diffusion, to increase the concentration of charge carriers to reduce the overpotential due to the bulk conductivity, and diffusion. So, a lot of research is still to be done.